So, like like I told you, addition polymer, and then for condensation polymer, we have learned like there are two types of linkages that are formed as a result of condensation polymer, ester linkage and then amide linkage. So today we are going to discuss uh, the different examples of polyesters, like in which you would see ester linkage, and polyamides in which you would see amide linkage. And also, before going to start this, I told you we have two types of polymers. You know, whenever the examiner would be asking to identify the monomers by looking at the polymer, so I told you that you have to see the sequence of this bond. As I told you that in this you have OCO, like the same sequence. Okay, it has the same sequence. I can write same sequence, but in this, if you can see, it has OCO, COO, OCO, COO, and OCO sequence. So if you have different sequence just like that like it's also a repeating sequence. So you can you can tell that your monomers are different. Like if you can see different monomer and then different monomer. One monomer is going to have carboxylic acid and this monomer is going to have alcohol. Okay, so if you are going to make this polymer, like the polymer which is formed by these two monomers, so I am getting this sequence OCO, like the different monomers, if you can see the different sequence. But if you have this monomer, single monomer having the two functional groups, alcohol and plus carboxylic acid. So if you have the same monomer which contains different functional group, so if you would be having the polymer, so you would see the same sequence just like that. Okay, OCO, OCO, and OCO. So if you can see OCO like the same sequence, so you can judge the monomer. You can determine the monomer. You can predict the monomer, that the monomer should be the single molecule which contain two different functional groups. That's an idea. Okay. So in today's class, we would be discussing uh, these are the questions that we did yesterday. Okay. In today's class, I would be telling you there are different examples of condensation polymers, including polyesters, polyamides, polypeptides, and polysaccharides. Okay. In polyesters, you would see you can say like the ester linkage. Okay, like it's sterilene. The example in which the esters would be there, it's sterilene. Then in nylon, you would see the amide linkage, that's called polyamide. And in protein, again, you would see the peptide bond, again the amide linkage. Okay, or they are formed by this, and this. Basically, I have shown the different monomers. Okay, if this is your polymer, so these are the monomers. If this is the polymer, so this is the monomer. If this is your polymer, so this is the monomer. If this is your polymer, so this is your monomer. So we would be discussing in detail how the examiner would be providing you these monomers and how you would be at, attaching them together to make a polymer. And we would see that what type of linkage is formed. Okay, so first of all, starting from polyesters, so obviously as the name indicates that they are going to have ester linkage, and the first example for the polyester is PET. PET boleto, you know, it's terylene. The common name for this polymer is terylene. Okay, so how can I form terylene And what are the reagents and conditions for this? Ultimately, the temperature should be 280 degrees Celsius specifically, and the catalyst should be antimony oxide. This is the catalyst, and this is your temperature. Okay, so in the presence of this temperature and a catalyst, when you would be joining them together, the first monomer is benzene 1,4 dicarboxylic acid, like it has two carboxylic acids, and then ethene 1, 2 diol. So this is your another monomer which contains alcohol as a functional group. Okay. Then when they would be combining together, ultimately, you know that we discussed the condensation polymer, in which I told you that there is a loss of a small molecule in the preparation of condensation polymer. Despite this, when you are going to prepare addition polymers, there is no loss of any small molecule. Like you will never see that the water is released, like the HCl is released. So condense, like the removal of a small molecule, whether it's water or anything else. Mostly it would be water, most of the time. Okay. So as I told you that the water is going to be removed when they are going to add. Okay, so same happened. It's OH and H would be removed, and the remaining rest of the molecule would be joining together to form this linkage. This is your ester linkage. This is your ester linkage. Ester linkage. Ester linkage. Ester linkage. Okay. Then it's steriline, so it has a rigid structure. Okay, because it has a benzene ring. Benzene ring, obviously, you have more carbon atoms. It's more stable. There is a delocalization in benzene ring, obviously. So ultimately, it would be having high melting and boiling point, and the strength of this polymer is high. And the strength of this polymer is high. So the examiner would be providing you the monomers that are 1,4 dicarboxylic acid and 1,2 diol. Then what you are supposed to do, then only you have to join them together, and obviously there would be the product that is called like the PET, like pterylene. Okay, so in this polymer, ester linkage is present. Okay, this is the most important thing. And then if you can see this, there is another polymer in which you would see the ester linkage, that is called polylactic acid, that is known as PLA. Okay, polylactic acid. So what are the monomers? What are the monomers of this polymer? So ultimately the monomer is 2-hydroxypropanoic acid. Ultimately the monomer is 2-hydroxypropanoic acid. So this is your monomer. If you can see the 2-hydroxypropanoic acid, so you can notice like this is a single monomer in which the two functional groups are present. This is the single monomer in which the two functional groups are present. Okay, so this is carboxylic acid and this is alcohol. Single monomer, single monomer contain the different functional groups. So I am supposed to mention this single monomer. Okay, containing different functional group. So when they would be joining together, ultimately I would say there is a loss of a small molecule, that is water in this case. Okay, so they are joined together. So this is the ester linkage that you can see right now. This is your ester linkage. So now you have more than one ester linkage. So that's why I would say that this is your polyester. Okay, this is your polyester. So this is another polymer in which we can see the linkage is an ester linkage. Okay. So basically, we have two polymers that have ester linkage that I told you. The first one is terylene, and then you have PLA. Okay, and then polyamides. Polyamides, obviously, as the name indicates, that they would be having amide linkage. Okay, there are two types of polyamide like polymers that have amide linkage. Ultimately, we have natural polymer as well, and then we have synthetic polymer. In synthetic polymer, specifically, we would be discussing Kevlar. That is very important, and then we would be discussing the nylon. The nylon. Starting from nylon, okay. So the monomers, obviously, whenever we would be discussing any of the polymer, we need monomer. Without monomer, how can you prepare the polymer? That's the main thing. Let's suppose if you have if you want to prepare ammonia, if you want to prepare ammonia, so means that you need nitrogen and hydrogen. Obviously, you need nitrogen and hydrogen, right? So ultimately, the nitrogen and hydrogens are you can just what can I say? Uh, you can just compare, okay, that these are the monomers. So if you are going to join them together, so you would be making ammonia. Same goes with the nylon 6,6. I want to make this polymer, I need monomers. Okay, so I would say that the first monomer to prepare nylon 6,6 is 1,6 diaminohexane, and the next monomer is hexane dioic acid. Hexane dioic acid. So this is the structure for 1,6 diaminohexane, and this is the structure for hexane dioic acid. So ultimately, again, I would be saying that the water would be released. The water would be released. Okay, the water would be released like plus H2O. The water is removed. Okay, the water is removed, and then rest of the molecules have joined together. Like you can see, this is your amide linkage, and the whole polymer is called nylon 6,6. Okay, this is an important polymer in the daily life as well, that it has a low density. First of all, if you remember, we used to discuss aluminium in IGCSE, and we used to tell you that aluminium has a low density, so that's why the high tension wires are made of aluminium due to their low density, right? So again, same goes for the nylon 6,6. Again, this is having a low density, but interestingly, it's very strong. But its elasticity is higher. It's very interesting. Elasticity is higher, but again, it's strong, just like a graphene. Graphene is a single layer of graphite, which is very strong, light in weight but very strong, because it's a giant covalent. A lot of covalent bonds are there between the carbon atoms. So same goes with this. It has a low density, and elasticity is higher, and the strength is also a good, which make it very useful fiber in clothing industry. Um, for climbing ropes, the rope is made of the nylon 6,6. Basically, it's a strong polymer. It's a strong polymer. Like, why this is very strong polymer? Like, if I'm going to climb any place by using this rope, which is made of nylon, so like, what makes it so much special that is very strong? How can I say that the nylon 6,6 is very strong? So I have shown in this diagram that These are the chains of nylon polymers. These are the chains of nylon polymers in which you can see the hydrogen bonding between the layers of nylon. Due to the presence of very strong hydrogen bond. Hopefully, you know that hydrogen bonding is a very strong intermolecular force. Okay, three types of intermolecular forces we have discussed. First one was like van der Waals force, or known as London force, or dispersion force, or IDID force. And the second force was permanent dipole, and the third force was hydrogen bond. Okay, so hydrogen bond is at the top of the line. So it is the strongest intermolecular force of attraction. So in this nylon, hydrogen bond is present, strong hydrogen bonds are present, and due to the presence of this very strong hydrogen bond, so it's like I'm talking about the nylon that is very strong. Okay, so basically we are going to compare the strength of any polymer with the bonding, obviously with the bonding. Okay, so then after this, we have Kevlar. Kevlar. Kevlar is also a polymer which contains amide linkage. Okay, so the monomers, ultimately, again I would say I need a monomer. Okay, again I would say I need monomers. So the first monomer which is used to prepare Kevlar is this diamine. It's diamine. Okay, it's what? It's diamine. It's dicarboxylic acid. Okay. It's dicarboxylic acid. When they would be joining together, water would be removed just like that. Amide linkage would be formed. This is the Kevlar polymer. This is the Kevlar polymer. This is the Kevlar polymer. Remember, okay? So again, the same thing. This is your Kevlar that is very strong and flexible. Why? Again, I would say hydrogen bond. Due to the hydrogen bond, due to its exceptional properties, like it contains a very strong hydrogen bond, and you can see how the hydrogen bonds are going to be shown in this structure. So a lot of hydrogen bonds you can see. So Kevlar is used in bulletproof jackets. It's used in bulletproof jackets because it's very strong due to hydrogen bonding. If you want to break it down, so you would not be able to do this because due to a lot of a lot of bonds are over there. So how can you break this? You would be breaking one bond, two bond, three bonds, four bond, a lot of bond. How can you break it? So this is the reason which makes it like the stronger polymer as compared to the other. And also, not only this, the wings of a fighter jet is also made of Kevlar. It's very interesting. Now you can have an idea that how much the Kevlar is stronger. How much the Kevlar is stronger, obviously. Then the third one is that latest tennis rackets are made of Kevlar. Again, I would say these uses are going to tell you that how much stronger the polymer is. And the last one is that fire protective clothing worn by F1 racers. You know, um, basically, in racing cars, due to accidents, they got a fire. So to save the person, they are supposed to they are supposed to wear the cloths. They are supposed to wear a cloth, okay, which should be fire protective, which should be fire protective. So fortunately, Kevlar is one of them. Why? Due to hydrogen bonding, due to strong hydrogen bonding, which makes it stronger, remember. Okay, and then we have biochemical polymers. Ultimately, you know that I mean protein. Proteins are made by the reaction of different amino acids. So the monomer for the protein is The monomer for the protein is amino acid. If you are going to join them together, so ultimately, which means that you are going to make protein. That's it. Okay, you are going to make protein. Simple. It's very simple. You are going to make protein. So I have taken this monomer that is called amino acid, and I have taken again the same monomer that is amino acid. It's a general polymer that I have taken because in this you can see R. R bole to any alkyl group. If you can see the data booklet, okay. So ultimately you will see over there that we have different R groups. We have different R groups. If you can see the data booklet, see this. Yes. So if CH3 is your R in the side chain of the, you can say, amino acid, okay, or you can say polymer, so I would say that this is alanine. And if R is CH2CO2H, I would say this is aspartic acid. Same goes for cysteine, glutamic acid, glycine, lysine, phenylalanine, serine, tyrosine, and then valine. Okay, so we have different monomers according to the presence of R groups. That's why I was saying. Okay, that's why I was saying. Also, uh, this is called peptide linkage. This is called peptide linkage. Again, the water is removed. Again, I can say water is removed as a side product or a byproduct, okay? And then, like the polyamide is formed. Polyamide is formed, right? So, and also each protein have unique sequence of amino acid. देखो obvious सी बात है ना, हर प्रोटीन का एक डिफरेंट सीक्वेंस होगा कि उसमें जो अमीनो एसिड्स अटैच्ड हैं, the fashion is different. The attachment का fashion is different for all the polymer, for all the proteins, okay? So this is the biochemical polymer, and after discussing these, after discussing these, uh, we need to do some, you can say, like the topical papers. Some of the questions we did, but some we have to do, okay? But before going to discuss some topical past papers, there is other thing that we need to discuss, okay? That is, you can say, which one is biodegradable and which one is non-biodegradable polymer. Can you tell me which one is biodegradable and which one is not? Yes. Hmm? Yes. Let me tell you, okay, condensation polymers are biodegradable polymers, remember, generally. So, biodegradable polymers. Biodegradable polymers. Okay. So, if the polymer is non-biodegradable, if the polymer is non-biodegradable, so remember that's the big problem to the with the environment, I can say. Okay, with the environment, I can say. So, like you know, biodegradable polymers are becoming more common. You know, before we used to use non-biodegradable polymer in maximum quantity. Like A common example is polythene bags. Very dangerous polymer. Polythene bags made of polyethylene. Ethene is the monomer and polythene is the polymer. Okay. So it was non-biodegradable, so it has multiple issues with the environment. So the polymer should be biodegradable so that it can degrade. It can you can say destroy, okay? And it's good to destroy, remember. Because as I told you that if the polymer is not biodegradable, when sun rays strike to these polymers, so they emit toxic radiations which are very dangerous for the environment. So that's why I'm saying. That's why I'm saying. Okay. So the first one is general. It's a general observation. It's a general observation. Polymers. Addition polymers are while condensation polymers are biodegradable. Okay हो गया जी. तो the thing is that के in condensation polymers their linkages are broken down. Remember, in condensation polymers their linkages are broken down. Their linkages are broken down. So when their linkages are broken down, ultimately I can say they are going to react. Ultimately I can say that they are going to react. Okay. So in condensation polymers, in condensation polymer, condensation polymer linkages that may be that may be ester or amide. Okay, breaks down. Therefore, I can say that these are biodegradable polymers. Okay, that's why I'm saying that these are biodegradable polymers. Okay, so also we were discussing how to identify the monomers by looking at the like polymer. Okay, let me tell you the recent paper in which the examiner has asked the question related to the polymers. Okay, so let me tell you something. I'm sending the paper. Wait, just wait. I'm sending the paper.